Hi everyone, welcome to the 136th MedAI group exchange sessions. This week we have Debesh Jha from the University of South Dakota talking about his research on advancing medical imaging. Um, Debesh is a visiting assistant professor in the Department of Computer Science at the South Dakota University. He's an IEEE senior member and was recognized amongst the top 2% of scientists worldwide by the prestigious Stanford and Elsevier ranking in artificial intelligence and biomedical engineering in 2024. His research interests include AI, machine learning, and their transformative applications in biomedical as well as clinical imaging. So, Debesh, thank you very much for joining us today. And before we start, do you have any preferences on how you'd like to take questions? Is it okay for us to interrupt you, or do you have some time at the end where you want us to ask questions?
Yeah, maybe we can do it at the end.
Okay, sounds good. So maybe if audience, you can hold your questions to the end, or maybe post it on chat. We can try to have it at the very end. So without further ado, let me hand it over to Debesh.
Yeah. Uh, thank you, Nandita, for such a nice introduction, and also thanks a lot for inviting me. So today I'm going to talk about my PhD postdoc and like some of my recent works. So from data to diagnosis, advancing medical imaging with curated dataset and AI algorithm. So let me start with the digestive system because we'll talk a lot about some of these. For example, here you can see organs from mouth to anus. So today, the reason I wanted to show this digestive system is like we'll talk about most of the cancer related to liver, stomach, pancreas, large intestine, small intestine, etc. And most of the cancer occur in the digestive tract. So, for example, SCC, pancreatic, colorectal cancer, stomach cancer, anal, and also rectum cancer, etc. So, this makes digestive system or digestive tract a hotspot for the cancer. That's why we would like to use AI to detect some of this so that we can save life at an early stage. Now let me move to some of the statics. So if you see to the Global Cancer Observatory statistic 2022 and based on the absolute number, so lung cancer is the most leading cause of the cancer, followed by the breast cancer, colorectal cancer, prostate cancer, stomach cancer, liver, and here are like top 15 cancers. And if you see the mortality rate, then again it is the lung cancer, colorectal cancer, liver cancer, breast cancer, stomach cancer, and so on. So from here, and if you compare from the past data, let's say from 2020 or 2018, the number of cancer incidence is increasing day by day. That's why we have to use certain tools or applications such as AI to detect cancer at the early stage so that we can save a lot of life. Now, let me show you some cancer incidence and mortality trend. So if you see like by continent wise, so you can see, for example, North America, Canada, Russia, China, etc. Uh, Even Europe, like Europe has the highest incidence of the cancer. But when you move to mortality rate, then you can see the largest number or highest number of mortality in Russia, Mongolia, for example, China, and also like some part of Europe, North America, etc. So there is no region that is left from the cancer, but as compared to the like European countries or North America, usually Southeast Asia or African countries, you can see they have lower number of incidents, and this might be also because of data collection issue and so on. But from here you can see like entire world there in the entire world there is like a lot of cancer. And if we talk about United States, the trend is similar. So you can see, for example, in male, the most leading cause of cancer is prostate, followed by lungs, colorectal, and for female it is breast, lung, colon, and so on. So some of these cancer occur like the trend is same as that of the other part of the world. So the good news is that we can save or some of this cancer, if detected at an early stage, we can completely cure it, or like there is a high chance that we can improve the survival rate. For example, breast cancer, colorectal cancer, stomach cancer, and also, for example, esophagus cancer. So we can cure it or at least prolong. For example, if there is a liver cancer or pancreatic cancer, we can prolong the stage. So, however, there are certain challenges in the medical imaging that I would like to discuss. First, because mostly today I'm going to discuss about medical imaging, for example, medical data collection and so on, and algorithm. So, one of the main challenges is small test data. So, and there is also data bias. For example, certain race or certain group might be underrepresented. And then we have issues such as quality issue, data quality issue. For example, most of the images we get even from the hospital are low resolution because hospital even do not want to share like the latest data with us. And there is also like evaluation issue in the community. For example, most of the like papers they rely on certain metrics like one metric, and there is also sometimes unfair comparison, and there are also challenges such as generalization and robustness challenge. For example, uh, models are sensitive to noise and artifacts, so the performance can change abruptly. So we need to develop, like for example, robust algorithm. Then there is challenges related to adversarial attack, where you, for example, you change one pixel and the result, like you can see the decrease in the performance of the result uh, abruptly. And there is also issue related to interobserver variability, where there is like disagreement between the two different radiologists, for example, and out of distribution samples. So this is also another like generalization issue. And domain shift, for example, when patient from, let's say, model trained on the United States is tested on model tested on the hospitals in Norway, for example, then it might not give the same result as that of like here. So this is like an example, some of the example of generalization and robustness issue. So, but the thing is, like, why are we discussing, like, as an AI scientist, why are we discussing radiology here? Because, yeah, mostly this is the work of the radiologist, not ours. But there are certain type of biases or certain type of yeah, biases that radiologists uh, face. For example, here are the top 10 biases that is listed on the paper from 2018 RSNA. And some of them are like anchoring biases, confirmation biases, satisfaction report, etc. But two, like I have highlighted two of these, like satisfaction of search and unintentional bias. And they have also provided like how can we mitigate this kind of biases. So yeah, we'll deal mostly on, we'll look at into it. So that's why I have highlighted some of these biases. So the reason, like satisfaction of search means like the doctor might be satisfied by just finding like few tumors, for example, in a whole long tumor. So this is an example of satisfaction of search. And we call our project is MedAtlas X, where we talk from data driven, like data curation, to uh, AI enhanced disease detection, and then again we standardize and benchmark. So we kind of like not only develop data, but we like this is kind of like our entire pipeline. So if you see here, so in data-driven data curation, AI-driven data curation, like we segment some of the anatomical structure, and then we try to find out some of the precise, like we give precise annotation. Then we use AI to diagnose, and then like it's all of us, we have been doing like lesion detection, segmentation, etc. And for some of the application where real-time decision support is important, so we also try to like develop algorithm that is real time. And then after that we also organize competition and challenge workshop, etc., where we give like where we showcase our or provide our novel data set, and other participants can develop method on it. So that, and we also try to cover different aspects like from the data so that they can develop like robust algorithm. And let's move on to data development for AI ready data set. So any data set like, or at least like the data set that we use for AI. So it start from initial planning, like where doctor write proposals and it requires ethical approval. Then doctor gets permission, and then you have to hire, like get patient consent and then hire patient, and then we have to anonymize all the data. Then we collect data, process, annotate it, label, and then it is passed through data inspector, where data inspector will inspect and validate for the quality assurance. Then you document it, pass through ethical and legal compliances, and then you can share the data. So this is like an outlook for the data, developing AI ready data. So while talking about this, now let me move to one of our recently developed dataset that is called cirrhosis MRI. So this is, we have submitted it to Nature Scientific Data, and it is under like consideration now. So cirrhosis MRI data consists of 628 MRIs. It has both T1 and T2 weighted MRIs, and it has also like, for example, mild, moderate to severe, like all the classes of liver cirrhosis. So you can see like the total number of patient is 339, where we have both T1 and T2 weighted. T1 weighted consists of 310, and T2 weighted consists of like 318 images. And you can see, for example, like the total number of patient is 339, but the number of images we have, or volumetric scan we have, is only 310 and 318. So like we get a lot of question related to this. So this is because some of the images were corrupted in between and we had to discard it. We could not use it for uh, into our data set. And the data set was collected from the Istanbul University, and the scanner used was 1.5 Tesla and 3 Tesla. And here is the link to the data set. So we have both T1 and T2. So this is like our annotation process. So you have the raw input, and then we annotate, and then we convert the data into information or intelligence. So this is an example of T1 weighted images, where you have like the T1 weighted is used to show the anatomical detail, uh, and where fat is suppressed. And then like both T1 weighted and T2 weighted has their different advantage. And that's why like we try to put both T1 and T2 weighted. So T1 weighted is better at morphological changes, to detect morphological or show morphological changes and detect contrast enhanced SCC. And it is also like useful for example, if you have to see vessel, for example. So T1 has this advantage, whereas T2 like you can see fluid. Here fluid appears bright and fat appears dark. So, and then this is used for higher contrast, and then this is especially used for grading like fibrotic or detecting fibrotic tissue. So this is annotation strategy for T2 weighted. And this is how like we annotate slice by slice. And then first of all, we get like DICOM images. So these are some of the information related to pre-processing DICOM images. And then we anonymize all the information, like for example, like scanner type, patient age, um, everything like that we can anonymize and convert it into like Nifty format. And then we use deep learning based for example, we use total segmenter or something, or our own algorithm to get um, uh, like segmentation, and then we again send this to the doctor, so at least we can save some amount of time while annotating the data set. So these are some of the state-of-the-art data set available in the community, and we release cirrhosis MRI data set. So if you check, like if you look into the table, there is no data set that is specifically designed for cirrhosis. So this is the first data set. Duke liver data set has some of the cirrhosis cases, but it is like basically liver MRI data set, and also number of patient is like less as compared to us. So Yeah, this is only data set available for liver cirrhosis segmentation. And then when we release some data set, we also set some of the benchmarking algorithm. So we compare with some of the state-of-the-art algorithm. And then this is algorithm from our group, like this one and this one. So we got the good results. As you can see here, for example, we achieved the dice coefficient of 87.89. So yes, and then this is for another like T2. And then here are some of the qualitative results. So we try to analyze, for example, mild to severe. And if you see here, so this like circle highlights the misdetection. For example, where the model fails. So still like our model is good. And for if you check for the severe cases, so I think all the model are failing to detect the severe cirrhotic liver, but still our model is better as compared to the other in the state of the art or other in the literature. And now this is all about the segmentation. But when we design segmentation dataset, we also thought of further extending the dataset into classification dataset. For example, like as a radiologist, they first segment the dataset and then grade it. For example, whether it is mild cirrhosis, moderate cirrhosis, or severe cirrhosis. So if we can develop that dataset, and it will be like useful for the community. So we further classified the data into mild, moderate, and severe, and also like for the both the modality, because it can help in treatment planning and also preventing complications. So this is like a CSV file that I took like a screenshot of. So here you have, for example, information related to patient ID, age, gender, radiological evaluation, and here like are the values like what it refers to. So we also benchmark using mild, moderate, and severe, using deep learning and radiomics-based approach, or radiomics and machine learning classification machine learning approach. And if you see the result, then I think like transformer-based approach like is usually the better for all of this. So now let's move on to our second data set. We call it peri-pancreatic edema dataset. So for some of you, like as a computer scientist, we might be wondering what is peri-pancreatic edema. So it is a condition where fluid accumulates in the tissue surrounding the pancreas. So for example, this is a pancreas, and it is a fluid like there, some fluids gets accumulated, and then the surrounding the pancreas, and it is early good like to detect, because it can lead to severe pancreatitis. So it is also the indicator of disease progression and helps to determine pancreatic severity. So, and it is hard to detect. So we develop a data set like that comprised of 255 patients, and then there were patients with edema and without edema, and then we made it open access to the community. And the annotation protocol is same as that of the liver cirrhosis. And this is how we have released it in the open OSF. And then we benchmark after we release the data set. So here, this is our city images, and we generate the label using linear TransUNet. And then once we generate the label, we extract the ROI, and then we give it to, for example, radiomix-based. We extract radiomix-based features, and also we give this ROI for deep learning, where you have CNN and transformer-based approach, and then we try to predict whether there is edema or there is no edema. So this is our result based on, again, radiomics-based approach and deep learning-based approach. So Swin Tiny achieved like a high accuracy of 97.95. So this is like some of the benchmark. Again, we released the third data set. We call it PEN-SEG data. So the data set consists of 767 MRI scan, 385 T1 and 382 T2. And there are some of the information related to from where the data is coming from. So we also made this data set open access. And this the annotation strategy for remains the same for T1 and T2. So yeah, So I have also tried to like arrange each of my data set into my web page where one can find all of these data set and experiment. So the reason behind showing all of this data set is once you have data set created, like once you can extract information and from the information you can extract some knowledge, then you can use it for several applications. So that's why data set collection or large scale data set collection is really important. So now let's move on to gastroenterology. So in gastroenterology, we'll mostly focus about colonoscopy. So colonoscopy is time demanding. It takes about 60 minutes for a colonoscopy and 30 minutes for upper GI endoscopy. So the miss rate is around 22 to 28% in the clinic, which means if 4 patients goes to the clinic, like for one of them, there is highly likely that they have missed the lesion. And there is a larger interobservability variability. And one in 24 women and one in 22 men are diagnosed with colorectal cancer, and these missed polyps can convert into cancerous, and the survival rate is very low if you find it at last stage, that is stage 4. However, the good news is like it is preventable completely if you can find it at the early stage. That's where AI can play an important role. So yeah, if the lesion is detected and removed at the precancerous stage, the mortality is 0. And CADEX here can play an extra pair of eyes or can act as an extra pair of eyes for the gastroenterologist working in the room. So this is some of the clinical procedure, picture of the clinical procedure. And the reason why uh, colorectal polyp is challenging because like if you see the surface looks same like polyp surface, like same as that of the mucosa, and there is also like low lightening, flare artifacts, etc. And also the size of the polyp or the structure of the polyp. For example, this is a flat polyp. Usually doctor miss polyp like this kind of polyp, which looks like a normal tissue. So there is a high miss rate because of this kind of regions. So again, uh, like our goal was to develop some data set. So when I started PhD, there were only limited data set, and most of the data set were like 5 or 6, and most of those data set were restricted. So no one, yeah, so almost like there was no open access data set. Then we started with data collection. So our goal was to develop classification data set and also segmentation data set. Uh, so at first, like usually we train the model, we collected this data set from Bærum Hospital in Norway. And then we separate, for example, polyp versus non-polyp. So let's say if you have 100K images, GI images, if you can separate it, you get, let's say 5,000K polyp. So from here, human annotator can play, like do it very quickly rather than exploring all these images, and then can label this kind of images and can create also segmentation map. So this is some of the example of the annotation we did. Uh, you can see. And then one of the data set that we recently released is gastrovision data set. We released like in 2023 in ICML workshop. So this is, yeah, this data set consists of, this is a multi-class data set, and it consists of 24 classes. So it has 8,000 images, and then it was collected from 3 different center, and here are like imaging equipment use, and it was like labeled by a team of gastroenterologists and computational scientists. So you can see class-wise detail. So you can see, for example, some of the class has a high number of images, whereas some of them are low, because this is also like how it, like, for example, some of the cancer might be rare or some of the classes can be rare. So it is difficult to balance all these images. And here are some of our benchmarking result. And we also make this data set open access for so that community can benefit from it. And then recently I have developed a new data set called PolypDB dataset. So this is also the first ever dataset that has images from different modalities. For example, we collect data from 5 modalities. One of them is BLI. Second modality is FICE. Third one is LCI, NBI, and white light. So all of these are different lighting modes, and there is no publicly dataset available that compromises of all of these modality. So in order to develop a generalizable model, I think we need images from all the modality. So once we we have made this dataset public, and the dataset consists of 3,934 still polyp images from four different centers, that is Berum Hospital in Norway, some hospital in Sweden, and also from Vietnam, two centers from Vietnam. And it contains images from these modalities. And it was annotated by a group of 8 gastroenterologists and some computational scientists. And then once we annotate or once we develop our data set, like we also provide some benchmarking. So you can see some of the segmentation benchmarking and detection benchmarking. So I'll not go into more detail. And so that community can benefit from it and can develop much better algorithm uh, than like the one we already benchmark. So these are some of the segmentation and detection result. Is the data set is coming from 3 centers or 4 centers. So we also did kind of like federated learning based segmentation. And then we also try to inject like some of the attack like FGSM attack into a network and see if like our data set is robust or against those kind of attack. So these are some of the benchmarking result for federated learning and adversarial attacks. And this is one of the popular data set I developed. So I will not talk a lot about this. This work was done in 2020, and this is one of the most used data set today. So for polyp segmentation and detection. And while developing the dataset, one key message that I learned was screen resolution can affect the quality of the annotation. So at first we started with the small screen, and then when we had some result, uh, when we had some result, then we showed to the doctor, and then we found that some of our annotation was wrong, and this was coming especially from the low resolution screen that we are using. After that, so once we developed this data set, so in the stage we learned that you need to have a larger screen, and so that you can at least find like all the pixel or annotate all the pixel in the images. And our this data set was indexed by Artificial Intelligence Index Report 2024. So it has been highlighted at several places, including this HAI report. And then we also released some of this data set like HyperKvasir data set. This is the world largest data set. And then we also did some effort like we applied some effort into video capsule endoscopy. So the goal of video capsule endoscopy data set, or like the main problem here, like that I want to highlight is, let's say you have a video like of 1 hour or more than, sometimes even 8 hours, because usually patients follow this camera and then record it for 8 hours. And then if you can use some video processing algorithm and then give the result in 5 minutes or 2 minutes, so it will help a doctor a lot. So this is the clinical problem, and we try to detect we try to perform some of the classification tasks. And then for now, like what I would like to say is this data set is publicly available. And then again, we release some of the data set in collaboration with University of Oslo. And these are some of our open source data set. And so after like after releasing the dataset or after developing some novel dataset, we also, in our addition to dataset development, we also organize some kind of like some challenges. So one of the effort was Medco challenge, and other effort was IndoCV 2021. So we have organized several challenges that lead to several publications. And here, like the challenge tasks, so we in different challenges we pose new tasks. So this is like uh, the challenge from 2020 and 2021. So you can see, for example, in Medco 2020, we pose tasks. One of them is polyp segmentation, another is algorithmic efficiency, because for colonoscopy, real time is important. So that's why we posed this challenge. And in third, like in second challenge, we added this transparency tasks. So these are sample data set from the for the challenge. And then we had many participants, and these are the like a result, or these are the algorithm. So this is the algorithm they have used. So you can see, for example, algorithm they have used, backbone, nature of their method, for example, whether it is cascade or whether it uses deep supervision, and choice basis, etc., whether they use augmentation, loss, etc. uh, so yeah, this is again the algorithm, like table for the another challenge. And then here you can see, like we also evaluate all of this, and then we rank like one, first, second, and third. So, and then we also make analysis, for example, where model fails. So this is like a failure case. So for example, here you have some small polyps. So this is like even here clinician fail for this kind of cases. So even if you see all the model, they fail for this to detect this kind of cases. So which means there is still some effort required to solve this task. And then this is another challenge, like result for the instrument tracking. And then based on different factors, for example, whether they publish their code open source, code quality, model evaluation, for example, whether if they perform failure analysis, evaluation, study explainability, and metrics they use. And also we incorporate human in the loop, or doctor in the loop. So doctor evaluate the result and also a report. So based on that, we give them final score. And these are other like BQA challenges that we organize. And then you can see, like we also sometimes give some award and publish it in journals. So for this kind of effort. And this is the paper for other challenge. So now let's move on to the algorithm. So this is the algorithm I developed in 2024 for MIDL. So this is our segmentation algorithm. We call it TransNetR. So here, if you see this, this network is an encoder-decoder architecture, and it uses ResNet 50 as an encoder. And then here, and yeah, so it uses ResNet 50 as an encoder, and then here the like features are extracted at different blocks, and then it is passed through uh, pass through decoder blocks such as like upsampling, and then you can concatenate the feature from the encoder, and then again pass it through the RT block. So RT block is the innovation here, which I would like to show. And then you follow the series for all of these, like two other block, and then upsample, and then you get the final output marks. So for the RT block, so here you have like input feature which is passed through one by one convolution, and then you perform operations such as batch normalization and liquid ReLU, and you pass it through the transformer encoder block for long-term dependency and also self-retention. So it improves the performance, and then pass through con one by one D, batch normalization, etc. So what we observed was, and then we did like out of distribution testing. So what we observed, like we got state-of-the-art result when we compare with the other architecture in the like literature for like both in distribution dataset and out of distribution dataset. So for here, in distribution means the dataset we trained, and out of distribution means the dataset that is captured using different scopes. For example, let's say you have in the training dataset you have Pentex, and then you use like for testing you use dataset capture using other center or other kind of scopes, etc. So we got better result. Then this is another algorithm I developed. So here, this is also an encoder-decoder network, and here we have this is almost based on RESTful block. So the input is passed through RESTful block, and then again passed through squeeze and excitation block, where the extracted feature gets squeezed and the useful information. It takes the useful information, whereas it excites the unuseful, suppresses the unuseful information. And then again, the feature is passed through residual block followed by squeeze and excitation block. And then you have SPP block in between encoder and decoder, which act as a bridge to enlarge the field of view of the filters. And then these features from the encoder is passed through attention block followed by upsampling. Here we use bilinear upsampling, and we concatenate, and here skip connection is used uh, to for example, especially we use skip connection for information propagation between like especially for back propagation, like and gradient flow. So this is like we have three encoder and three decoder, and then we again pass it through SPP followed by contouring and segment, and we get some output. And this was developed in 2019, and this architecture become like quite popular. So this is old citation. Uh, and it was state of the art, and then it was mostly used for polyp segmentation as a benchmark. We further improve with by using TTA, like test time augmentation and conditional random field, and then we even improve the performance of the ResUNet plus plus, and we showed for different data set, including video polyp data set, and we got some improvement, like a huge improvement. And this is so this slide is interesting because yeah, this was my initial work, and when I showed this slide to doctor, so for example, for this kind of cases and this kind of cases, so these are like easy to detect polyp, so anyone can detect, like know it is a polyp or it is a colorectal cancer. But for the cases like this, um, so for the cases like this, where this is the ground truth, none other model could detect it, and ResUNet plus plus could detect it. So it has some clinical significance. Um, this is also a reason why it become more popular. And then yeah, we further try to check the performance in challenging scenario, like whether you have, like for example, some frame has one polyp, multiple polyp, and so on, and how model performs. So still it is not perfect, but better than the other. And we also did some generalizability study where we trained the model on one data set and tested it across a new data set from different distribution. Uh, and we saw like this after adding TTA and conditional random field, we obtain better result. And then let's move on to another architecture, that is DoubleUNet. So this is the architecture I proposed in 2020. So from its name itself, you can see it has like network 1 and network 2. So it uses like 2 unit. So the input is passed through BGG19 encoder, and then the feature are extracted. So all these hierarchical features that are extracted are passed through ASPP. And then the feature from ASPP is passed through different decoder block, and then you get the output. So here what we do is like we get this output, and again we take input from here, multiply them uh, so that we can get like a better input, and then again we pass it through the second encoder, like second network, so which means second encoder, and then here SPP act is a bridge between encoder and decoder, and we get the output 2, and again we can concatenate the output 1 and output 2, and we get the refined output. So this this architecture showed state-of-the-art performance in 4 dataset, and this architecture was really strong. And then until like 2022, 2023, like it was top on the leaderboard. And the third architecture I developed was ColonSegNet. So the main goal to develop this architecture was to develop like, for example, lightweight model. We instead of taking the input like 256 by 256, we try to increase the resolution. Like we take 512 by 512, and then we pass through residual block, and then which is again passed through stratified convolution, where you get like, for example, 256 into 256. So like divide by 2. Again, we pass through residual block, and then we perform max pooling, where again you downsample the features by factor of 2. So you reduce it to like by factor of 4, for example, like basically, and then again pass through convolution. So it has two encoder and two decoder block. And instead of using, for example, we use upsampling or bilinear upsampling in ResUNet++, here we use transpose convolution because we also want the model to learn because the model is already lightweight. So we use transpose convolution of factor 4, and then again like the same thing goes here. So the process follows and then you get the output. So this architecture, like in terms of result, it was not the best. So you can see here, but the processing speed was really high. And then we also got some of like at the same time qualitative and quantitative results. It was also promising. So this architecture is being used by NVIDIA for their colonoscopy sample app, and I think it is mostly because of it lightweightness, and also it has like it has a good performance or decent performance, I mean. So now let's move on to my other architecture on abdominal organ segmentation. So recently, like this paper will be presented in ICAS 2025. So here, like we have an input, we pass it through, and we call it multi-decoder network. So we call it multi-decoder because there is 3 decoder in our network: decoder 1, decoder 2, and decoder 3. And then, so here the input is passed through MIT B2, where you get like features, and these features are again passed through, like this is like encoder, and here this act is a bridge MSFED block, that is multi-scale fusion. So like if you see here, instead of like F1, these features that is like it is passed to dilated convolution, but all of this here we perform feature multi-scale feature fusion. So it is passed through multi-scale feature fusion, which is again passed through, for example, decoder block. You get the output 1 from the decoder 1, and then so again here the key idea is like we get output 1 again. So you can see some over segmentation here. So we'll use this output 1 as an input to the other decoder or other network, and then we add max attention block here to highlight the most important regions, and then we are trying to refine the output, and we do the same. And finally, here you see like this over segmentation here is removed. So that's why, like, because we use different decoders, so we call it multi-decoder network. Uh, so these are some of the qualitative results on liver and spleen. And then again, we got a high performance. So you can see, for example, MDNet can get 93, which is like better than others, but at the same time, like we cannot improve a lot because this is already at like 90s. It is difficult to improve the uh, result. And these are some of the results. So you can see like from the MDNet. And recently we presented this paper called SAM Mamba. So here, what we use, we try to take the advantage of both SAM and Mamba state space model. So here, input image is passed through SAM encoder, where you can see like we freeze this one, and then this is again passed through Mamba. Like output of this one is passed through Mamba prior, where basically the goal here, like for the Mamba prior is you try to improve or contextual information. So for contextual information or context-aware information, so you try to improve this. We use Mamba prior here, which is again passed through adapter. So here is the adapter architecture. Like you have VITs. So basically, we through this adapter, we want to improve the performance of or we want to improve VIT inside the SAM architecture. And this is like using this one, you generate serial marks, and you also have the prompt encoder in the encoder, and then you pass it through the decoder, and then you get the output. So basically, yeah, here we use Mamba for to improve this contextual understanding. So Mamba is used here. And this is like our overall architecture from Mamba. And then we compare with some of the state-of-the-art architecture, and we got the better result. And this was published in WACB 2025 this year. And this is like some of the results. So if you see with compare the ground truth with other model. So for example, UNet plus plus or other model, they fail. They show, for example, this model show our segmentation, and sometime also under segmentation a model can show, but our model is optimal. And this shows the learning. For example, you have input which is passed through like encoder extracted features, then you get like encoder extracted mass, and this shows the refinement through the decoder. And we can compare with the ground truth, and like at least for these cases it is quite good. And then we saw some of the evaluation result where we saw the strength of the method. And here I have some video. So you can see like some polyp detection result. So model can identify polyp, but you at the same time you can also see some of the false positive, right? So this is some of the example like of practical application of our approach. So even the model is able to find out this small polyp. This might be a false positive. So yeah, this is another demo for the segmentation. So the model is able to detect or segment polyp like with a high accuracy. Yeah, you can see some of the false positive, so we don't want those. And this is demo, sorry. Okay, so it's difficult to play this one. So we move to other. So this is like, so when we release data, like we also release source code for all of our architecture. And despite, and in addition to like developing some architectures data set, we also work on the ethical side or ethical aspect of AI, especially for example, generative AI and so on, because it is also really important. So yeah, these are some of our works. And here, like this is a clean image, and you have the ground truth, and this is the clean prediction from the unit. And we inject some noise using inject some noise here, and then you can see like and then we gave it to our radiologist. So when radiologists compare this image and this image, they could not find the difference between original and injected like noise injected image. But when we use the same algorithm, the prediction was really bad. So this is due to adversarial attack. So we also try to like work on this kind of domain. And then, for example, we generated some image using diffusion model. So you can see some of the real images and synthetic image. And then we try to compare the performance. Like we try to run the model on real image and synthetic image. So you can see like our model was better for the real than real plus synthetic, for example. And when developing like a data using a diffusion model, for example, stable diffusion, it also incorporates some of the real information, and sometimes it might also degrade the model performance. So this is our learning from like some of our studies. And then, yeah, as you can see, like we have published some of the paper related to ethical aspect of AI. And now I'd like to show some of the ongoing effort, that is uh, development of comprehensive data set for dental analysis using panoramic X-ray. So you can see, so we are trying to segment, like for example, impacted tooth, pearl, and other classes, so that we could develop automated tool for dentistry. Similarly, we are also trying to work on we are working on dual energy CT denoising, where the goal is to develop like this is a high um, contrast image or high like better quality image, and this is a low quality. So here one has to emit like higher amount of radiation dose, here low. So if we can improve this one and make the quality of this image is like this one, for example, the one on the left, then image processing approach or like our computer vision approach can play a great role. And then we could also prevent some of the hospital resources. So this is another task. Third task we are working is on radiation therapy, where the goal is to like not only goal is to help in treatment planning. So this shows like, for example, gross tumor volume, planning tumor volume, uh, etc. And also we want to find out, for example, local failure. We want to do local failure analysis. So yeah, this is my conclusion slide. Deep learning in radiology is promising approach. The challenges in the application of deep learning is also challenge, like we have seen, is unique. And there should be close collaboration between the radiologist and computer scientists. So here I did not talk much, like we have another ongoing project where we incorporate like radiologist in the loop. Uh, and then the use of semi-supervised and unsupervised learning approach can also play, like help improve the model performance. So this is uh, all from my side. Thank you very much for listening.
Thank you so much, Debesh. And we would like to, before we move on to the questions, we would like to ask the audience to extend a round of applause for this very amazing talk. And with that, the floor is open to questions.
Oh, thank you, Devesh. This is Shiva here. I think I have a couple of questions, and I have a great thing that I have used your couple of your datasets, gastrovision datasets. I have used it, and it's fantastic. I mean, I would say so. But I
Thank
have
you.
a couple of questions, like your, how do you manage this? Because when the instrument goes through this large intestine, there is always chance of occlusion, some kind of glow effect. You mentioned there's always kind of colonization issues. So how do you handle that? Like, I'm just interested to know, like.
Mhm. So how do we handle like those in our deep
Uh,
learning
uh,
based algorithm?
yeah, yeah.
For those kind of, so I think for those kind of images, so one of the approaches is just like data augmentation. We cannot do much
Mm-hmm.
for those, but the more we have, I think the model can learn
Mm-hmm.
uh, such kind of cases.
Yeah.
And
Yeah.
there is some cases, for example, like for example, bowel cleaning, etc., would
Mm-hmm.
play important role. So it is also like not only dependent to it is also depending to bowel quality. If you get better quality, then you can have like more detection rate.
Mm-hmm. I think there is a data set called bowel
Yeah,
preparation.
yeah,
That's,
yeah,
yeah, but that's not much data sets. I
yeah.
mean, I have one, sorry, I mean, if somebody is there,
Yeah.
then I have a couple of
Mm.
questions also.
You can go ahead, ask.
In annotations, is there any radiologist or like GI people from GI clinicians involved in this, or you just try to find out the segmentation and just put a writing bounding box, and through which you can find the coordinates, and then you apply it for the training
You mean like okay,
annotation
so
process?
for the annotation, usually at first, like when I started this work in PhD, so we had doctor in our teams, so who help us. So I used to annotate each and every image myself, and then I used to go to doctor, and then they used to check. And like from our experience, sometime even clinician they missed, and deep learning was able to identify it. So we during our re-annotation, like re-evaluation process, we found it, and then we again cleaned our data set.
Okay. Okay, that's all. Yeah.
Thank you.
Mm, thank
Are there any more questions? If not, I would like to ask Devesh, like, what do you see in future? Like, where do you go from here with all this data sets that you have and all these segmentation models that you built? Like, where do you see, like, what do you have in future for these set of like suite of models for and the data sets that you have?
Yeah, now if you talk about colonoscopy, for example, when we were doing like let's say when we started the project in 2019, 2020, like there was no FDA approved algorithm or like system, but now you have some of FDA approved system and they're already in the market. So it is also like I think we also have some influence on those kind of thing. So yeah, some of them already got FDA approval. Some of them could not. Some of them also donated some data to us. So that like, but when we tested, let's say when our doctor tested those models, even FDA approved models, they find like they say this is like an initial stage, and there are a lot of things. For example, here I showed you mostly related to diagnosis, but um, for treatment side, there is a lot of scope where we could work on. And for, let's say, liver cirrhosis, like I showed, so these are like initial effort. There is no data set in the community. And if there is no data set, there will be like no AI-based algorithm. And especially for the data one I showed you, like edema data set. So we have seen a lot of interest, especially from radiologists from China, because like computer vision, people usually like we don't know much about like what some specific term, right? So somehow we have to advertise it, like get people use it, and then we can reach to like optimal goal.
And I also wanted to understand, like, I think towards the beginning of your talk, you have talked about this domain shift, right? That, you have data sets that are kind of collected in Norway, and then whether if you're applying that model. So, how do you plan to deal with that? Like, how do you have models that already generalize those things? Well, like, I'm just curious.
Yes, so I think we develop, for example, yeah, here I just wanted to keep it because like different things. So I did not go into very detail, but we try to test it, for example, the model trained from Spain and test it on US and vice versa. So
Okay.
we got like a good result for that one. Like close to 90s or 85
Okay.
90, between 85 and 90, so which is like a good, but at the same time, like even we talk a lot about data set and we say like we use the term large scale, but we don't know like exactly what is large scale.
Yeah.
So yeah.
Yeah. Thank you so much for answering
Mm.
my questions. If there are no more questions, I would again like our listeners to kind of extend another round of applause for our speaker today. And with that, thank you so much, Debesh, for this really good and awesome and interesting talk, and for the depth and breadth of your research that you've worked on. So, with that, we would like to close today's MedAI session. Thank you, everyone.
Yeah, thank you very much for inviting. Bye.